So let's start with the new chapter, current electricity. I have just heard that you couldn't finish the capacitors topic. So I'd be taking up capacitors after we finish this chapter. We have ample time for this chapter. Okay, so we would be saving some time and finishing capacitors in the remaining time. So just a second. What is current? Actually, current can be used, this word current can be used for a lot of things. Water current and a lot of other currents, right? So electric current, that's why we say it, we call it electric current. What is this? Flow of charge. Huh? And can you be a little more specific? Flow of electrons. I would the rate of, while most of the time define current as Q by T, the average value would be different, and one example of this situation is AC. Yes, the average value 0 for one cycle, but the instantaneous value is not 0, right? There are other cases as well, so we would discuss these cases there and then. Okay, so let's start. For our discussion right now, average and instantaneous values are equal, right? So before we start any further, current and anything else, let's discuss types of materials. Okay, one would be conductors, one would be insulators, and the third one would be semiconductors. You know them. Conductors, yeah, they have free electrons, solid conductors. Okay, in fact, for a bigger picture I would write they have free charge carriers. Okay, so for metals the charge carriers would be electrons. For ionic solutions, the ions. For ionized gases, the ions and electrons, and so on. Is it okay? So they have free charge carriers. Sorry, they don't have, and they have partially. Okay, partial arrangement they have. Semiconductors are something in between the conductors and insulators. Is it okay? Semiconductors have some free charge carriers at room temperature, but not as much as the metals or the conductors. Is it okay? Free charged carriers, yes, in ions, ionic solutions. Na solution NaCl dissolved in water. Na positive is a charge carrier and Cl negative is a charge carrier. Same thing. Electrolytes are the same thing. They have ions as charge carriers. Okay. In fact, electrolyte is a better term for our use, because not every ionic solution can furnish free ions. Electrolytes can actually furnish free ions. Electrolytes are those salts which furnish free ions in solution, right? So these are the type of conductors, okay, on the basis of availability of charge carriers. Is it okay? So let's move further. Can I erase all this? We would recap it slightly, the semiconductor part. You have a full chapter on this at last, book 2 ka, I think it is the second last chapter, right? So we would have a full chapter for semiconductors, but we would still study slight portion of it, okay, after we are done with Ohm's law. Is it okay? So let's start further now. Do you know what is drift velocity? What is drift velocity? So now, drift velocity, let's study the microscopic picture, okay, and you will be able to understand what drift velocity is. Let's say this is a conductor, I have magnified it to, okay, I have magnified it using a microscope, let us assume it, and let us say this is connected to a battery. What actually happens? In a metallic conductor, you have positive ions and free electrons. Okay, this thing is called electron C model, right? In chemistry, you have studied it. Okay, not kiya nahi kiya. Solid states mein you must have done this. That ions occupy fixed positions called they form a pattern called a lattice. Okay, so conductors have very clear cut lattice structures. Okay, so ions are fixed at their positions while the electrons are to move. At 0 Kelvin, what happens? The electrons don't have, at room temperature, there is a zigzag motion. We call it thermal motion, right? So due to this thermal motion, the electrons, they go here and there. Let's say the connection is not complete right now. Okay, when we connect it to a battery, the battery establishes an electric field from positive to negative. Is it okay? Battery establishes an electric field from positive to negative, and because of this electric field, every electron experiences a force QE. Sorry, EE I should be writing, Q is E here, EE. Due to this electric field, every electron experiences electric force EE. Because of this, okay, I am erasing this a little bit so that things are clear. Okay, because of this electric force, just imagine electron which was moving in a straight lined zigzag path. Please note, it is a straight lined zigzag path. Straight lined, okay, between two collisions its path is a straight line. Okay, okay, and after collision it is like it bends in some direction. This is before I connect a battery. Now after I connect a battery, a force acts in this direction. Is it okay? It is a constant force. Okay, the velocity of electron is at an angle to the constant force. Can you remember we studied this kind of scenario in 11th as well? Just glance, just recall, try to recall it. We studied one thing called projectile. Projectile was nothing but velocity, an object with some initial velocity and a constant force, always acting on it. The path was what? Parabolic. So its path would be parabolic, something like this, something like this. So between two collisions it would now cover a parabolic path and it will try to move toward the positive terminal. Positive, is it okay? Okay. After switch is connected, you might have studied about it, right? So at 0 Kelvin, nobody is moving. You apply electric field, they simply move in the direction you want them to move. But at room temperature, what happens? They are continuously in this zigzag kind of motion. So apart from this zigzag motion and or the thermal motion, they will have some drift motion as well. Explain the shift of the electron. Okay. Yes, exactly. I'll explain. You remember this in the projectile. We gave some initial velocity to the particle, and because of the continuous force because of earth, continuous gravitational force Fg, the path was parabolic. Now just imagine, in this scenario the electron is experiencing electric force in this direction continuously, a constant force acting all the time. So it will try to bend the path in this manner. Okay, this was downward, so path was bent toward the downward direction. This is a leftward force. Okay, so path would be bent in the leftward direction. So as you can see, between two collisions the particle would bend away, bend leftward basically. So there is a shift in the path. Okay, there is a basically shift in the collision point, you can say. Okay, between two collisions the particle drifts leftward. Okay, this is called this this velocity involved in this scenario is called drift velocity. Is it okay? Drift velocity would be nothing but dx by dt, rate of drifting per unit time. Okay, but you need not go into this detail, you just need to understand why it's happening. Somebody is asking some doubt. Okay, no, I'll explain that, don't worry. Okay, so this was the thing. Is it okay? Now just try to understand, initially when no switch was there, in no switch state all the electrons were doing zigzag motion, but there was no current. Please listen to me carefully. When no switch was connected, okay, when the circuit was broken, in this scenario through the conductor all the electrons were moving here and there, zigzag motion, all were doing zigzag motion, but there was no current. So all electrons moving but zigzag, but I equal to 0, right? From this we can simply say that actually what is happening, all the time after t time they would have some different velocity. Okay, so I'll write here, let's say first electron collides after t1 time. Okay, its collision it is at t1 time. So just before the collision its velocity would be v vector is equal to u1 vector plus a t1. See, a would be same. Why the direction of flow of electric current is opposite to that of electrons? Because conventionally we take positive charge, the direction of positive charge as the direction of current. It's convention, you can take it in the reverse direction, but then you would have to rewrite all the laws of electricity and magnetism. So to avoid that, we taking the conventional direction of current. Okay, there is no logic involved, it's just that kiya to kiya was, right? So v vector would be u1 vector plus minus e by m t1, not t1 के ऊपर नहीं इधर. Okay, this is the velocity of first electron. We can write the velocity of second electron, third, fourth and so on. What if we take average? Let's say for nth electron, right? If we take average, now if we take average, okay, average velocity, so v average would be how much? V average would be how much? Sum of all the velocities, है ना? u1 plus u2 till un upon n minus e by m t1 plus t2 upon n. Is it okay? What is this value? 0. We just discussed that the average thermal velocity would be 0 because some is moving, some are moving in the left, then some are moving in the right. So this thing would go and we would have velocity as minus e by m. This time is what? Average of all the collision times. That's why we call it average relaxation time. Okay, the time during which electron relaxes because during collision it's not relaxing definitely, it would be experiencing great amount of force. You know collisions involve great amount of force, right? Okay. So this is average relaxation time tau, and this is the drift speed Vd. Okay, that's how we reach this whole of the thing. I said average relaxation time. You know, T1 was the time of collision, was the collision time for first, T2 was the collision time for second electron, and so on. So I'm adding them up. This is average collision time. Average collision time, सबका time का sum किया by n. That's it. Is it okay? Huh, you can say this is the average drift velocity. It means if all of them collided at the same time always, then all of them would have this velocity always just before collision. That's drift velocity. Yeah, when you don't connect the battery, acceleration would be 0. They would be moving with thermal speeds, and these thermal speeds are of order 10 raised to power 6. They are of order 10 raised to power, while the drift speed here would be some few centimeters or maybe millimeters per second. Okay, but it's just that these, you know, thermal speeds, they don't contribute to anything. When drift velocity is coming, see, when you know, when any body is moving, acceleration can be applied to it as well, while when the body is at rest, it can be applied to that body as well. You know, ऐसा तो नहीं होता ना, you cannot say that if a body is moving, I cannot apply a force on it. Since it is experiencing force, whether it is at rest or it is in motion, it would still experience this acceleration, whatever the state may be, कुछ भी हो. Acceleration तो अभी हमेशा होगा ही, right? Acceleration would always be there. Clear? Point clear? Okay. So that's how we reach this. Drift. There is no drifting. In absence of electric field, there is no drifting. Means electrons are not going toward the left direction or the right direction. They are doing zigzag thing. If some are going toward left, then some other electrons would be going toward right. Is it okay? Okay, I'll sum this up. What happens at 0 Kelvin? No motion. Electrons रुके मस्त बैठे. As temperature rises, because of thermal energy, the electrons move, okay, in zigzag motion. At room temperature, the thermal motion, the thermal velocity is actually pretty high at room temperature. It's pretty high. It's 10 raised to power 6. But you know, the total is 0 always, because you know, if some are going toward right, some other would be going toward left. Okay. हाँ, बट इसका मतलब क्या होता है? जब बैटरी कनेक्टेड नहीं है तो करंट 0 है. इसका मतलब इक्वल इलेक्ट्रॉन्स ही जा रहे होंगे ना. अगर लेफ्ट ज्यादा इलेक्ट्रॉन जा रहे होते तो करंट होता लेफ्टवर्ड, राइट? if the current is 0, it means, you know, no net movement of electrons is there. Getting my point? Net movement. Okay, no net movement of electrons is there, because if there had been a net movement, means in some direction more number of electrons are traveling, so current would have been there in the opposite direction, right? What? I didn't get your point. Yeah, every electron would at electric field 0. That would be, you know, if you start considering the atomic electric fields, okay, that interaction and all, you know, that then there would be acceleration for some portions, retardations for some portions. We cannot go into that much microscopic thing, right? मूवमेंट तो इसलिए हो रहा है बिकॉज दे हैव सम थर्मल एनर्जी, because of thermal energy, and this energy they would keep always. Okay, imagine gas molecules, are they accelerated always? Gas molecules in this room, are they accelerated? They are not accelerated at all. They are hitting the, the floor, the ceiling, everywhere they are hitting our bodies, but they are rebounding with same velocity, right? They are rebounding with same velocity all the time, same speed actually all the time. They are keeping their energy constant. So that's the kind of case here with electrons. Can I erase this? So relation between I and Vd, let's check this out. This is a conductor whose cross sectional area is A, okay. N is the electron density. Electron density matlab number of electrons per unit volume. Per unit volume, is it okay? Number of electrons per unit volume. So number of electrons upon volume. Let's say L is the conductor. Is it okay? Okay. So let's find out the number of electrons in this. Okay. N is the electron density. So total number of electrons would be taking a negative sign here because the direction of flow of current and Vd is opposite. So that's why there would be a positive sign. What? They charge nahi, they flow through bulk of the conductor. If you have no at electrostatics wala scenario, there would be in surface, there would be at surface. See, in electrostatics I'll explain what happens. I think this is a cylinder, just attach a positively, this is something you studied from NCERT, just attached a positive plate here and a negative plate here, positive metallic plate, negative metallic plate on two corners. These electrons, they rush. Okay, why? Because there is an electric field established in this manner. So these electrons, they rush and they neutralize everything. Is it okay? Okay. So this state is not final state, it's not the steady state, it is what? Intermediate state, when the electrons are rushing, and finally inside the conductor E would be 0. What happens in current electricity, that we maintain this electric field using a battery. We supply fresh positive and negative charges all the time using a battery. So it would never be a scenario of electrostatics. Electric field would never be 0 inside, and that's why there would always be a flow of electrons unless the battery dies. Okay. So can I erase this? From this you can check, this is NAE. Vd is how much? How much is Vd? This would be N actually I'm doing a mistake. It should be minus sign here, and that's why a positive here. That's why positive here. Okay, minus sign would be there. I used the correct explanation, but I wrote the wrong signs. VD and current are opposite. If current flows in this direction, VD is always opposite. Electrons drift in opposite manner, right? The electrons drift in opposite manner. The current here would be this thing. Let's work on this one. Let's work on this thing. Can I erase this portion? At least I can erase this one, right? So current would be NAE square tau by M, and electric field can be written as V by L. Okay, so V is equal to ML by something like this. Okay, I separated A. I shifted everything from this side to that side, and I separated L and A. Is it okay? You can check. These are the same values. So what happens? This whole thing is called resistivity, property of the medium. L by A into I. This thing is called current. R into I. This is what? Ohm's law. Okay. So we, from the microscopic picture we studied, we derived Ohm's law. Is it okay? Can I erase this? तो हो गया होगा कितना? How much time do you need? Can I erase this? Now check. There is a thing called current density. What is current density? J is I by A. Basically, if this is a conductor and this much is the cross section A, if this much is the cross section A, I current is flowing. Current density is current per unit area. Is it okay? It is a vector quantity. So I will define a unit vector. Let's call it A cap. So it would have a direction A cap. Is it okay? A cap is a unit vector perpendicular to area along current. Is it okay? A cap is a unit vector along current. Okay. So if we don't take a perpendicular surface, we take some inclined kind of surface. Okay. Let's say this surface has angle theta with the perpendicular direction. So you can actually see that amount of current flowing through this smaller area is actually equal to the amount of current flowing through this, and the current density through both of them would be same. So if this portion has area A dash, this portion would have area A dash cos theta. Do you know how? This one has area vector this A dash. Take horizontal component. This horizontal component represents this portion. Is it okay? Okay. So in this case, the current density would be I by A cos theta, A dash cos theta, whatever you may call it. So I can be defined as J. If I take the magnitude, it would be something like this. I is defined as J A dash cos theta or J dot A. Okay, current is defined as dot product of what? Area vector and current density, right? So if the current through a surface is current through a cross section is not constant, here I assume that same amount of current is flowing through all the portions. So I can write this kind of thing. If something is like this, that this small portion is having a current, this small portion dA is having a current density J vector, some other portion dA1, some other portion is having a current density J2 vector, some dA2 portion. So what do we need to do is find the current due to this portion. How much would be the current due to this portion? It would be I dI1 is equal to J1 dot dA1. For this it would be dI2 is equal to J2 dot dA2 and so on, and we need to integrate, right? So the current here would be integral J dot dA. If the current density is not same everywhere, so you cannot find current directly by multiplying J into A, you need to integrate it. Okay, you need to find current through a small portion and then integrate it. Yeah, only perpendicular area. So a question on this. Yes. See, here I said if current density is not constant, if current density is variable through the surface, through the cross section, okay, some portions are carrying more current, some portions are carrying less current. ऐसा हो सकता है, ऐसा नहीं है कि ऐसा नहीं हो सकता. What if you form an alloy, you try to form an alloy, and in some portions it is not homogeneous. It's not homogeneous. You accidentally made a very heterogeneous kind of alloy. Inner portions have a lot of copper, outer portions have lot of some other tin, lead, whatever high resistivity metal. So what happens through the inner portion, the high copper portion, you would have a lot of current flowing. From the outer portions, lesser current. So it can be done, not difficult thing. So तो general लोगे. Let's have a question for this. I'll draw a bigger figure so that so this is a point P, current density through point P. Point P is at a distance r from center, right? Point P at distance r from center is J is equal to AR. Is it okay? So as radius increases, current density increases. The radius of the wire is capital R. So you need to find total current. Okay, find total current. P point is inside at a distance small r. Small r is less than the radius. So how to approach it? You need to take a small area dA. What type of area would you take in this situation? dA means kaisa? A circle, a ring, a square. You need to take a ring here because current density depends on radius. So all the points which are on the same radius, I mean all the points which are at same distance would have same current density. So it would be easier that way. So front view, if I, this is the side view, if I see from the front view, the point P is somewhere here at a distance r. Is it okay? So if you take a circle of radius r, all these points have same current density. Okay? So you need to consider a thin ring. Circle में inner, if we take whole of this circle, at this point the current density is 0. As you go out, the current density increases. How can you take, what value would you take for current density? That's why you need to take a ring. Okay? I explained the logic for a ring. I hope you understood. You need to take a ring of radius r and thickness dr. Okay? For this very small thickness, we assume that current density would not change appreciably. Is it okay? Okay? That for this very small thickness, the current density would still be AR. Okay? It will not increase a lot. So for this very thin portion, current density is same everywhere. So we can use what? JDA. Okay? So the current flowing through this small ring, this kind of ring is there. Okay? The current flowing through this small ring, thin ring, is JDA. And how much is the area of this thin ring? 2 pi r dr. We discussed it last time. So this would be AR into 2 pi r dr. If you want to find current, you can integrate and find out the answer. आंसर आया? The current would be integral of this thing. So this would be A 2 pi r cube by 3. R square नहीं होगा, cube हो जाएगा, integral. Is it okay? Okay, shall we continue? So we knew that V is equal to rho L by A into current, right? Can I write rho V by L is equal to rho I by A? This thing is electric field, this thing is rho J. Can I write J is 1 by rho into E? This thing is called sigma E. And since these two quantities are, vectors, so I am representing them as vectors. This is called microscopic Ohm's law, right? I hope I can raise the left half. So this was all the thing which you already knew. Some 5-10% addition from my side, but I was assuming that you knew all this, and I am assuming, in fact, itna to pata tha, right? So let's start. further. Can I erase this? Let's start now. So, you know current, it is rate of flow of charge, no longer charge by time. It is dq by dt, right? Okay. For steady state, it is q by t. You can take q by t, you can take dq by dt. It's one and the same thing. Is it okay? Okay. We understood that the flow of electrons, the current is because of flow of electrons in case of solid metals. If there are ions, so obviously it would be because of flow of both the ions, positive or negative ions. Is it okay? It would be the current would be because of flow of both the ions. So we would be considering mostly solid conductors, metals, okay, or alloys, etc. So I would not go any further on electrolytes, ionized gases, and so on. So you studied that for solid conductors, what happens? Electrons at room temperature do zigzag motion, okay, for which the net displacement is 0, okay. But when an electric field is applied, they, along with their zigzag motion, they start bending toward the positive portion, yeah, opposite to electric field, yeah. They start bending toward the positive end or opposite to electric field. Is it okay? Because of that bending, they show a shift in position, right? This is called drifting, and the velocity in this scenario is called drift velocity, right? So we discussed drift velocity in terms of relaxation time, okay, and we discussed current in terms of drift velocity, as well as current in terms of voltage, Ohm's law, right? Okay, so let's proceed further from here. What is this thing? This is resistance. This is rho L by. Resistance is a constant of proportionality which depends on length and area. Is it okay? So we will discuss about resistivity a little later. First let's consider it in terms of L and A. Why resistance depends on L and why it depends on A. Resistance is the obstruction to flow of electrons. You have been studying this since 10th, right? So what happens? Let's say this is a conductor, okay. Some current I was flowing through it, okay. Now if it has length L, current is I. What if I attach another conductor of same length L? What happens when length doubles? The electrons which had to cover L length, now they have to cover 2L length. They would take double the time. So the charge flowing would be same, but time taken to cover would be doubled, right? That's why current becomes half, or we can say obstruction doubles, okay. Another way of thinking about this is, if the length increases, more number of collisions, the electron has to experience more number of collisions before reaching the positive end. So that's why it will take more time, and so less current, right? What about area? What happens when we increase the area? We increase the size. Let's say this has area A, current I is flowing, and battery is here, okay. What if I connect another cylinder here of same area A? It would still carry current I. Let's combine them. Let's match them and form a conductor of area 2A. It would definitely carry current 2I now, right? Obstruction becomes half, okay. So adding area, increasing the area means like you are adding one more conductor in parallel. It's like you are adding one more conductor in parallel. So the original conductor would carry I current, and the extra conductor would still carry I current more. Is it okay? Okay. So another way of thinking about it is, imagine pipes carrying water, same tank, but if you connect a thin pipe, it would definitely bring less water. If you connect a thicker pipe, it would definitely bring more water. Okay, it's a game of capacity. A thicker wire would have more capacity. It can carry more charge carriers. That's why current increases. Okay, is it okay? So, yes. Charge half नहीं हुआ. Charge half नहीं हुआ. I said current is charge upon time. For constant current I am using. This is same, this doubles. What would be current? What would be current? It would become half, obviously. नहीं, ऐसे सोचने पे भी तो देखो, the current density remains same. It's a copper wire, let's imagine, and you attach another copper wire. The current density would remain same. You have the same battery. You have the same battery. So what other factor changed apart from this? Now the electrons have to travel longer path. That's it. If everything else is same, the number of charge carriers is same. So the charge available is still the same. Remember, we calculated charge was NALE. Okay. In fact, for this the charge doubles. For total, the charge doubles. But what happens? They need to travel double distance. Plus, additionally, if I connect battery, initially the electric field was V by L. Now the electric field would be V by 2L. So two factors. Even if total charge increases, two factors come in: double time and lesser electric field. So they would move slower, take a lot more time. Okay. So this is, you need to know only in qualitative terms. You need not know it in numeric terms or something like that. So I'll erase this. I'll explain one thing, that if a wire is stretched by n times the new length, if a wire is stretched by n times the new length, L dash would be NL, but amount of metal would still be same, right?
Yes, sir.
Volume of metal would be same. So volume of metal remains same. So volume, which is AL, area into length, cross sectional area into length, would be A dash L dash. So A dash would be A into L by L dash, which is A by N. So area becomes n times less to keep the volume same. What about resistance? It would be rho L dash by A dash, rho L NL by A by N. It is N square rho L by A, which is N square original resistance. So if you double the length of wire, its resistance becomes 4 times. If you make it triple, if you triple its length, 9 times. I'll repeat it. Let's say we stretch the wire to n times, right? So the new length would be NL. Is it okay? But you are not adding any metal. You are just stretching it. Imagine a rubber band. When you stretch it, its cross-sectional area reduces. The amount of rubber remains same, right? So if you stretch the wire, the volume of metal remains same. Still same amount of metal is there. So it would now, the wire would become thinner. So volume is same. We compare the volume in two situations. Initially it was area of cross section into length. Now it is A dash L dash. So we find A dash. Okay. We know L dash is actually, if you don't get this, it is AL upon NL. This is A by N. Length is A by N. So for the rest, I calculated it straightforward. Can I erase this? You know, you can think of it in the reverse manner. If we melt the wire and form a thicker wire, if we form a thicker wire, so its resistance would become 1 by n square times. Is it okay? So do I need to write that? You can understand it. हो जाएगा क्या? For thicker wire, yeah. If a wire is made n times the original cross section, okay, you can understand it. It's exactly opposite. Please note, if the radius is changed by n times, the area would be changed by n square times. So there would be a factor of 4, power 4. Is it okay? If the radius is doubled, area would become 4 times pi r square. Okay? And if area becomes 4 times, then resistance would become 16 times, 1 by 16 times. Okay? One more thing. If wire is stretched by x%, okay, where x is smaller than 5%, okay, small percentage, thoda sa khicha, what happens? If a wire is stretched by x%, the new length would be L into 1 plus x by 100. होगा ना? पक्का? Simple interest, compound interest formula यही use करते थे. 1 plus r by 100, right? So same thing. So the new length would be this. What about new area? The new area would be reduced by the same factor. The new area would be reduced by the same factor because volume is same logic. Okay. So the new resistance would be rho L dash by A dash, rho L 1 plus x by 100 upon A upon 1 plus x by 100. And it would become, I will erase this portion, it would become rho L by A into 1 plus x by 100 ka square. And since this is a small percentage, you can use binomial, so it would be 1 plus 2x by 100. So resistance increases by 2x percent. Okay, 2x percent, which means if the wire is stretched by 1%, the resistance changes by 2%. 2%, 1%. Is it okay? This is valid only for smaller percentages. If the length changes by 50%, you cannot use it. Use the direct formula, that is finding the new area and finding the new resistance. Don't use it. Don't use the shortcut. तो कैसे करेंगे? नई लेंथ निकालो। नहीं, हर जगह इंटीग्रेशन नहीं घुसाना होता. Let's say the length of wire increases by 10%. So if the new length is, let's say original length is 10 meter, the new length would be 11 meter, obviously. Or can I say 1.1 L? The new length would be 1.1 L. So the new area would be A upon 1.1. Okay? Utna times reduce hoga. So the new resistance would be, you can solve it any further, L dash upon A dash. So it would be rho 1.1 L by A upon 1.1. This 1.1 goes up, it forms a square. You need to find the value. So even for 10%, it would be, if you find it, rho L by A into 1.21. So the factor is only 21%. For 10% increase in length, the resistance increases by 21%. So even now, it's okay. But the problem comes when you start using this kind of thing for 50%. If the length increases by 50%, it would become 1.5 times. The area would reduce by 1.5 times. Okay? And in that case, the resistance will not increase by 2x, yani 100%. It would increase by 125%. You can solve it. So don't use it for larger percentages. For smaller ones, it's fine. Okay? Can I erase? At least I can erase the left portion, right? Okay. Now, resistivity. What is resistivity? Resistivity or specific resistance? क्या? हाँ. Resistivity or specific resistance, it is the property of a material, है ना? Due to which it obstructs flow of electrons. Okay. So you can understand resistivity is property of material. It means if I make a copper wire of circular shape or a square shape, or if I make a thick copper block, they would all have same resistivity. So bending, breaking, remolding and all doesn't affect resistivity. You are very sure of that? Okay. Because they keep asking this in boards, that wire is length of wire is doubled. So what would be new resistivity? Somehow people keep using this formula, R is equal to rho L by A. They assume that this is same. Since length is doubled, they say that okay, resistivity would become half. So that resistance is same. But actually the resistance is no longer same. You stretch a wire, its resistance changes, not resistivity, right? So on what factor does resistivity depend? Nature of material and temperature. So dependence of rho on temperature. This is absolute temperature actually. हम Kelvin temperature की बात कर रहे हैं. ठीक है? We are talking of Kelvin temperature. Let resistivity of a material be rho naught at 0 degree Celsius. 0 degree Celsius or 273 Kelvin. Okay? Resistivity ये है. Let at T temperature resistivity be rho. At some temperature resistivity is rho. Is it okay? Let temperature be increased by dt. अब टेम्परेचर थोड़ा सा बढ़ा, you increase temperature, what happens? Resistivity increases. Is it okay? So the increase in resistivity d rho is directly proportional to the change in temperature. Okay. Somebody is asking about how can we calculate for greater percentage. You need to actually find the square. Here we used binomial. At this step we used binomial. But if the percentage is larger, you actually need to find the square. You cannot use binomial directly. Bas, that's the difference. The procedure is same. Okay. So increase in resistivity is proportional to change in temperature. I say increase in resistivity is equal to alpha dt, where alpha is a constant of proportionality. अच्छा नहीं sorry थोड़ा सा I missed one point. I'll erase this. Actually, you know, this board is cluttered with a lots of stuff. Now please, the resistivity is proportional to change in temperature. It is proportional to original resistivity as well. Originally ज़्यादा होगी, so change would be more. Change would be more. You combine them, you get new change in resistivity is equal to alpha rho dt. Alpha is constant of proportionality. Called temperature coefficient of resistivity. Temperature coefficient of resistivity, right? Okay. So now d rho upon rho is equal to alpha dt. Let's integrate it to find the new resistivity. Original resistivity was rho naught, final resistivity is rho. Original temperature was, let's call it T naught, final is T. Okay, T naught, 273 Kelvin. Okay, so this thing would be ln rho somebody asked, you told that if we stretch wire by x%, where x is less than 5%, then new resistance increases by 2x%. So we can, can't we directly multiply 1.1 x in the example you gave? No, you cannot, because for larger resistance, for larger percentages, binomial is not applicable. You already know that in binomial, the second term is very small as compared to 1. We apply binomial, we write this thing, we apply binomial when x is very small compared to 1. Only when x is very small compared to 1, only then we apply binomial. If x is large, this portion, you know, we used x by 100. If x is large, this square would have what? 3 terms. We cannot neglect the third term. We just wrote that this is 1 plus 2x by 100. What about the third term, x square by 100, x square by 10,000? What about the third term, x square by 10,000? If x is large, we cannot neglect this third term. That's why for larger percentages, you actually need to find the square. Okay, you cannot simply report that, okay, 2x% increase. Okay, so let's continue. The increase in the change in resistivity of a material depends on original resistivity as well as change in temperature. So using this logic, we continue like this. Okay, d rho is alpha rho dt. Okay, and the rho comes in denominator, and this would become ln. While alpha we assume constant, temperature dt integrated would become this. So this is ln rho minus ln rho naught. This is alpha t minus t naught, and this is ln rho upon rho naught. You know this property of log? This is alpha delta t. Take ln on the other side and you get rho upon rho naught is e raised to power alpha delta t. And rho is rho naught e raised to power alpha delta t. So this is the original expression. The expression which we study in NCERT is actually a easier version. If alpha delta t is very small compared to 1, if alpha delta t is very small compared to 1, okay, then we can use what? That rho is equal to, if you remember, Ex has an expansion of this type, right? So if the power is very small, so the expansion would be limited till this point only. Why? Because x square, x cube, they would be neglected, right? Okay, so this would become rho naught 1 plus alpha delta t. This is the form you studied. So the form you studied is valid only when alpha delta t is small. Okay, somebody asked, repeat the topic, and I say how I raised half of it. Okay, I'll continue. I'll repeat it. I said, resistivity depends on temperature, right? So as temperature increases, resistivity increases, more obstruction. The reason for that is, I didn't tell you the reason because I was waiting for this to get over. The reason for, just hold on. The reason for this, change in resistivity, the reason for this change in resistivity is that as temperature increases, the ions which were fixed, they start vibrating. And the electrons also, their thermal speed increases. Okay, more thermal speed means they will cover the distance quickly in lesser time. Is it okay? They will cover the distance between two ions in lesser time. So they get less time to drift now. They get less time to bend their path. Is it okay? That's why lesser drifting, lesser drift velocity. Okay. So the root cause is, reduction in relaxation time because they get lesser time between two collisions. And in that time, it is that. दोनों ही चीजें एंटी हो गई ना, दोनों ही चीजें अगेंस्ट हो गई ना, don't you think? I was saying, okay, because of collisions, because of increase in temperature, time increases. Okay, time decreases, sorry, relaxation time decreases. They get less time between two collisions. It is that time during which they were bending their path. Now they are able to bend their path lesser, less drifting, less drift velocity, right? Okay, number of collisions increases, same effect, less relaxation time. Is it okay? That was the reason. So now increase in resistivity depends on original resistivity as well as the change in temperature. Why? Because original resistivity, if somebody has more resistivity initially, it would have more increase as well, a larger increase. So I combine these two factors, rho dt, and I get how much? D rho is proportional to rho dt. Please note the proportionality and alpha, they look identical, but they are not. Okay. So I introduce a equality, and this is a constant of proportionality called temperature coefficient of resistivity. Okay. Okay. I assume alpha to be constant, rho I bring in the denominator, and then I integrate. This is ln, so I get ln rho minus ln rho naught, which is ln a minus ln b is ln a by b. Okay, this form. On the other side, you can see it's straightforward. Okay. Somebody asked that would alpha depend on temperature? Yes, it depends on temperature. Here we assumed alpha to be constant, but if it is not constant, we need to replace the actual expression of alpha in this. Is it okay? The actual expression of alpha in this situation. Here I assumed alpha to be constant, and that's why I actually did what? I brought alpha out of integral. The situation based, because in one question it was asked that alpha is 1 by T. Alpha is 1 by T, the absolute temperature. So you need to find the new resistivity. So you can replace this 1 by T, it would become some ln kind of thing once again. Is it okay? So it all depends on the value there, okay, the situation. It will depend on nature of material, and it may depend on temperature or may not. Is it okay? So it's like not a very fixed kind of value. It varies with temperature. Alpha varies with temperature. It is not steady. So for some portion we can assume alpha to be constant, and we can derive this thing. Is it okay? Can I increase? Can I erase it?
Yes, sir.
Increase कह रहा हूँ मैं. किस पे इंक्रीज होगी, डिक्रीज होगी, किस में? For which type of material? For conductors, no. For insulators, yes. For semiconductors, yes. You can make them in this manner. High बना भी सकते हो, low resistivity alloys भी बना सकते हो. हाँ. Chemical properties. It's like it cannot be explained using physics here. Right? Chemical properties. Up you mix two metals, maybe because the size of ions is different. Maybe because size of ions is different, so more number of collisions, or maybe you get lesser free electrons now. Is it okay? So that's why. With? Why? When we increase temperature. I am a little confused. You asked that why resistance increases with increase, resistivity increases with increase in temperature. I just explained that with increase in temperature, in the thermal velocity increases. So now more number of collisions. The ions are still fixed. Electron gets lesser time to travel from one ion to other ion. Okay, so time between two collisions now decreases, which in case of insulators something else happens. You asked conductors, so I was explaining conductors. I'll explain, don't worry. So here I would like to add some important point. Those conductors which follow Ohm's law are called ohmic conductors. Not all of them are ohmic. Is it okay? Not all of them are ohmic. So some non-ohmic वाले check करो. For ohmic, VI graph is a straight line, but for a semiconductor for a silicon diode, diode is some instrument, some device, okay, it is like this. And on the negative side, if you keep increasing negative voltage, the current is 0. Okay, so it is non-ohmic. It is not giving you V proportional to I curve. It is not giving you. Okay. This is a semiconductor, silicon diode. For ionic solutions, yes, which even for ionic solutions, what happens? For ionic solutions or for insulators, you increase voltage, current remains almost constant, then after some time it suddenly increases, surges. Okay, after some voltage, okay, sorry, ulta ho gaya, it should be like IV, and it should be also IV. Now here you increase voltage, current remains 0, and after some voltage the current increases. Here also you increase voltage, current remains 0, but after some voltage it suddenly increases. What happens in these scenarios, that after some voltage, you know, I'll explain this later. This is for this ionic solution or for insulators. Okay, this actually this breakdown voltage is very high voltage, 10 raised to power 5 volt ke type ki. Okay, what happens at this voltage? The electrons are ejected out of the metals, the the atoms, the bonds. Is it okay? In insulators, what happens at very high voltages? The electrons are ejected, zabardasti खींच लिए जाते हैं. They are, you know, forcibly withdrawn from the bonds. So now the bonds are incomplete. They act as holes. They act as spots for electrons to sit. They conduct. Okay, the electrons also who became free also conduct. Is it okay? The electrons also conduct. Okay. कहाँ किसमें? ये this is the curve for semiconductor. तो उसकी रेजिस्टिविटी बढ़ी कहाँ? कम हो गई उसकी तो टेम्परेचर. It's not ohmic. These two graphs are, you know, not following this all derivation. They are non-ohmic. They don't follow Ohm's law. So we cannot find resistance for them using the same V by I thing. Second graph is for insulators. For ionic, you know, the breakdown voltage is not that high. Ions, if free ions are there, so even for small voltage they would allow. Actually, you know, it's like way back and then it falls. Suddenly it drops totally. नहीं ऐसा दिखाया ना. हाँ वो you will see when you reach the chapter semiconductors, you will see that NCERT में जो इस chapter में बताया गया है वो पूरा correct तो नहीं है. वहाँ पे बिल्कुल सही बताया गया. You can check that for a diode what kind of graph is there. Okay, so don't extend it to negative portion, बस अभी for the positive portion. Okay, because you know there then so many questions come into our mind कि ये कैसे हो गया. Hole actually is a term used in semiconductors. Okay, so holes are like, you know, if out of a bond an electron is pulled, so now this bond is incomplete, it needs one electron, we call it hole, gadda. If you put an electron, it's finished now. Okay, so now a question is this. a wire has resistance 1 ohm at 20 degrees Celsius, at what temperature will it have 1.2 ohm resistance if its resistivity is 5 into 10 raised to power minus 5 ohm meter. Is it okay? You can check the value is low, so you can use the normal formula, right? You can use the normal formula. Okay, and you already know the the pattern. If resistivity is written like this, resistance can also be written like this, right? I gave resistance here, not resistivity, right? So do it quickly, please. Acha, I didn't give alpha. Acha, actually this is alpha itself. It is alpha itself. Okay, the unit would be per Kelvin. Okay, it is alpha itself because you don't need resistivity for this. How much is the answer? तो बहुत बड़ा आ रहा है 5020 केल्विन ठीक आ रहा है फिर हाँ ठीक है हाँ इतनी आसानी से टेम्परेचर मतलब रेजिस्टेंस इंक्रीज नहीं होती है सो एक्चुअली just listen what I'm saying. Nichrome, manganese, constantin alloys, these are alloys used in electrical instruments. Why? They have very low temperature coefficient, this kind of low, 10 raised to power minus 5. So while you are doing experiment, the temperature the resistivity will not increase Okay, that's what I wanted to show here. Okay, this is the kind of resistivity of nichrome. For normal, it is 10 raised to power minus 2. Copper के लिए it is of the order 10 raised to power minus 2. So now let's discuss 1.2 is equal to 1 plus alpha delta t. So alpha is 4 into 10 raised to power minus 5. Delta t is t minus 20. Is it okay? So minus 1 is 4 into 10 raised to power minus 5, t minus 20. Okay, so t minus 20 is 0.2 upon 4 into 10 raised to power minus 5. Right, so this is 2, this is 5000. Is it okay? So temperature is 520
degrees Celsius.
Very high value. Okay, now let's change the question. A wire has resistance 10 ohms at 0 degrees Celsius. If its alpha is equal to 1 by 273 per Kelvin, find its resistance at 273 degree Celsius. Okay, so now this time alpha is no, not variable, it is constant. It is not 1 by t, it is 1 by 273, still a numeric value. It's large. You can check alpha delta t would give you 1. Alpha delta t would give you value 1. 1 is not a small value. We used this formula when alpha delta t was very small compared to 1. This time it's not. So find the value, use the correct formula. Much, yes, yes. It's like kind of, you can just consider this, that in not an issue. No. Yes. We have to use this.
Alpha delta t. So alpha delta t 1
This is 10 E 1 by 273 into 273. Nahi. This is 10 e ki power 1, which is 10 into 2.713. So the new resistance is 27.13 ohms. Is it okay? Okay. From that formula, you would have calculated the value to be 20 only. From that formula, from this type of formula, the value would have come out to be 20, which is not correct. Yes. ln r, just a second, you said ln r upon 10 is equal to 1. So take ln here, it will become r upon 10 is equal to e raised to power 1. the same thing. Okay, log on the other side becomes exponent. Have you actually studied this? Log कहाँ पे पढ़ा है? कैसे? बस properties, exponential series देखिए, log और exponential का inverse relation.
पता है कि inverse होते हैं एक दूसरे को graph
You didn't study inverse functions, did you? Functions हुए हैं?
अभी हुआ पिछली क्लास में
हाँ?
अभी हुआ पिछली क्लास में सर ग्राफ्स प्रोवाइडेड फंक्शंस के
Functions में inverse functions नाम की चीज़ भी होती है.
तो
Inverse trigo नहीं, not inverse trigonometric functions.
एक्सपोनेंशियल और
Log के and they are mirror images. तो फिर ये पता होना चाहिए था तुम्हें कि ln को उधर लेके जाते हैं तो it becomes ex. ln y is x, so y is equal to ex. They are what, inverse of each other? But temperature given is in Celsius and alpha is in Kelvin, so why will we not? Because the problem is delta T is original temperature is 0 degree or 273 Kelvin. New temperature is 273 degrees Celsius or 546 Kelvin. So this is 546 minus 273, which is actually 273 itself. That's why I didn't convert, because the temperature difference on Celsius scale as well as Kelvin scale is same. The temperature difference on Celsius scale as well as Kelvin scale is same. Okay, 10 degree change in temperature is equal to 10 degree change in Kelvin temperature, 10 Kelvin change in temperature. Is it okay? That's why. So how can we know that which of the two formula of resistance to be applied? You need to multiply alpha with delta T. If alpha delta T is a big value compared to, if is a value comparable to 1, you cannot apply that formula, the easier wala. If alpha delta T is very small compared to 1, it is let's say 1 by 100 type of thing, you can directly go with this one. Okay? Okay, so that's all for today's session. We'll continue this next time.